Hello, this is MAT221, Calculus 1. This is Mrs. Johnson. Today we talk about the fundamental theorem of calculus, which is section 5.3 of our textbook. We talk about the basics of where calculus was founded upon. So remember when we started talking about this idea of integrals. We talked about an indefinite integral first, and then we started in the last section talking about definite integrals, where this was our integration symbol. The lower number here stood for our lower limit of integration. Our upper number there stood for the upper limit of integration. The function that sits next to that squiggle, that sits next to that integration symbol, any function that sits next to that is called an integrand. And recall, any function that sits next to an integration symbol is thought of as a derivative function. No matter what it's called, we always think of it as a derivative function of the antiderivative that we find. So this symbol, any function sitting next to it, we think of as a derivative. And then dx was our variable. It was actually called a dummy variable. The reason why they call it a dummy variable is because in this particular case, when we're talking about definite integrals, it really doesn't matter so much what the variable is, it matters what the function is, because we're finding the area under a function. So we could call this function f of x, we could call this function f of t, we could call this function f of r, we could call it f of x. It really doesn't matter what the variable is here. What matters is what the function looks like on the graph to find the area between the curve and the x-axis. So this is our notation for the definite integral, and we used rectangular approximation methods in section 5.1 to evaluate these, but there is a newer and better way that Leibniz and Newton discovered of how to evaluate these integrals exactly. Now remember, when we find a definite integral, we're finding the accumulated amount of change of the antiderivative over a given interval. What we find here is a number. It tells us how much does the antiderivative function rise or fall over the given interval. So the practical definition of definite integral says that the area underneath the curve as a definite integral, if y equals f of x is a non-negative integrable over a closed interval from a to b, then the area underneath the curve of this function from a to b is considered the integral from a to b. Now we said this in the last section, where if the integral or if the function lies above the x-axis, this would be a non-negative or positive value, and if the function lies below the x-axis, this integral would be a negative number, just because of what we know from derivatives earlier in our course in units 1, 2, and 3, and even in unit 4. So the area under the curve is going to equal this definite integral. Now we saw that if a velocity curve, which remember is a derivative curve, if we had a curve and we could find the distance traveled by finding the area underneath the curve. For instance, in this case, if the velocity is given in meters per second and the velocity curve is given as this curve right here, velocity equals 1/2 t plus 1, we could graph it easily on our calculator or on our piece of paper, and then we could break this up into pieces to find the distance that this object is traveling in these 4 seconds. Because it's a nice straight curve, we could break it up into pieces and say, okay, this is a rectangle and a triangle. I could find this area exactly because it's a really nice curve. So I could say, well, the area of the rectangle is 4 units by 1 unit. So that area of this rectangle here would be 4 units. And the area of the triangle, which is 4 units by 2 units, but remember the area of a triangle is 1/2 base times height, so the base was 4, the height was 2, so this would be 4 units also. Adding these two together, we get, well, the distance I've traveled here in these 4 seconds is 8 meters because I've gone 4 seconds here in my velocity curve. Now, this was nice. We did this in section 5.2, where we talked about the definite integral as area. But what happens when the area is not easily found with geometric shapes? Well, we used rectangular approximation methods in section 5.1 and 5.2. So we used LRAMs, RRAMs, and MRAMs to estimate what that value is. But there is an exact way to find the area underneath a curved curve, and that is the fundamental theorem of calculus. This is the foundation that we'll use for integration. It says, the fundamental theorem of calculus says that if f is a continuous function on a closed interval from a to b, and if there is an antiderivative, capital F is any continuous antiderivative of the given function little f, and capital F is defined on the same interval from a to b, then the definite integral from a to b of little f dx is equal to the antiderivative function evaluated at the upper bound minus the antiderivative function evaluated at the lower bound. So that blue box is the fundamental theorem of calculus. Why is this called so fundamental here is Newton and Leibniz discovered that I can find the exact area underneath the curve if I can find the antiderivative of the given curve. And then all I have to do is evaluate the antiderivative and subtract. It was simply arithmetic. It was evaluating and subtracting. Very simple to do without calculators or computers. So remember that capital F is the antiderivative of the given function here. Remember, any function that sits next to that squiggle, that integration symbol, that function is always considered a derivative. So we're finding the antiderivative of that function and then just evaluating it at the upper bound of the integral and the lower bound, and then subtracting. And we're going to get a number. And that number is the accumulated amount of change of the antiderivative over this given interval. Now, there are different notations that are used sometimes in textbooks or on Google or even in WebAssign when you're talking about using the evaluation theorem or this part of the fundamental theorem of calculus. Sometimes they use this bar, and all it means is this. So in other words, if we use the notation capital F of x with this bar from a to b, it simply means evaluate the antiderivative at the upper bound minus evaluating the antiderivative at the lower bound. So this bar simply means this subtraction. So knowing that, sometimes books and Google and different sites will rewrite the fundamental theorem of calculus to look like this. But remember, it's the same thing, which is replacing here. So it says the definite integral from a to b of the derivative function is equal to the antiderivative function evaluated from b to a. So they'll put the two notations together. Remember that the derivative of capital F is little f. Remember, any function that sits next to that integration is a derivative function. These are other two common notations that sometimes are used on WebAssign, but again, they mean the same thing. It means evaluating the antiderivative at the upper and lower bound and subtracting them. So let's look at an example. If I asked you to find the area underneath this curve using the fundamental theorem of calculus from 1 to 2. So what we could do here, and remember this area is, the area here is positive, so I don't have to do any manipulation here. So what I want is I want that area, the area underneath the curve from a to b, in this case from 1 to 2. So really what they're asking me is find the definite integral of x squared, which is little f of x here, from 1 to 2. So my first step is to find the antiderivative. So the antiderivative of x squared, which we did in section 4.8 when we talked about indefinite integrals, we found antiderivatives. So the antiderivative of x squared would be 1/3 x to the third plus c. Now notice in this case, we don't add the plus c, because when we do the subtraction of the fundamental theorem of calculus, the c's are just going to cancel out. We're going to evaluate this function at the upper bound of 2, right? This would be this part of it, and then we're going to subtract the evaluating this antiderivative at the lower bound of 1, where we put 1 in for x here. But then if I had a plus c here and a plus c here, I would subtract them and the c's would cancel. So when we do the fundamental theorem, we almost never write down the c there. We do always include it, however, when we're finding the indefinite integral, where I don't have bounds and I don't have a number as my answer. So evaluating here, I did 1/3 2 cubed minus 1/3 1 cubed. And then we're just going to do the math here. So this part would be 8/3, and this would be 1/3. 8/3 minus 1/3 is equal to 7/3. Now remember, when we're doing this, we're finding the area of this case was really from 0 to 2, and this one was the area from 0 to 1, and then we subtracted them to get the blue area that we want, which is 7/3. So the area underneath this curve from 1 to 2 is equal to 7/3. This is miraculous here. We can find the area underneath the curve simply by using the antiderivative and subtraction. And our answer is not an approximation like we had with the rams. Our answer is the exact answer. Now, we could do this same problem, finding the area underneath the curve from 1 to 2 using the TI 83 or 84 calculator. And I'm going to stop my video so I can get this up and going to show you how we could also do this on the calculator. So here's my TI emulator here, so I can show you this, how to do this on the calculator too. So the first thing we would do is we would go into our y equals screen and put our function, which in this case was x squared. Then we would graph this function. So I'm just going to graph it in a normal screen. I just adjust my screen there a little bit so you could see the whole function. So here's my function, but I only want to look at the function over here. So I'm actually going to set the window. So I'm only looking from 0 to 3. And then graph this. So we only want to look at this function over here. Now it doesn't really look like the PowerPoint that much because my range, let's fix my range too. My range was only like from, oops, I didn't do that right. I'm going to put the right thing here. My range was really only from 0 to 2, I think, or 0 to 4. I'll put it that way. All right, it looks more like my PowerPoint, something like this, right? So here's my function. I want to know what is my area here from 1 to 2. So on the calculator, it's really simple to do. What we do is we go to the calculate menu. So we do second and then calculate. And it brings up our calculate menu, and you can see from number 7 here, we can calculate, there's the definite integral. So if we hit number 7, it prompts us, well, what's your lower limit? Where do you want to integrate from? And I just type 1 and then hit enter. And then it prompts me again, well, what's your upper limit? And my upper limit in this case was 2, and then hit enter. And notice it will shade it in for us and then calculate the actual definite integral, which we figured out, remember, was 7/3, which is 2 1/3, which is exactly what we have here. So this is an easy way to do this area underneath the curve, this definite integral on the calculator also, using the second calculate and then just using this definite integral button here on your calculator. So I'm going to stop my video here and we'll start our next video going on to the next example.